PDF file of these PowerPoints have already been posted, so you can check that. Okay, so let's look at chapter number 1, Introduction to Control Systems. And as I mentioned earlier, a control system, control engineering, what you're doing is you are taking different fields of engineering, specifically electrical, electronics engineering, mechanical engineering. And when the control systems, the theory of control system and control systems were created, there was no computer science or computer engineering. When the computer engineering started taking place, it was under electrical engineering. So usually the control systems used to call mechatronic system, that is mechanical and electronic system. But now, of course, control system is comprised of mechanical, electrical, electronics, and programming. So programming, of course, if you're using some hardware, some microcontroller or something, then that is part of the electrical system. But now we, of course, the software that you're running on that, or the code that you're running, that also becomes the third leg of the control system. So you have mechanical, electrical, and you're programming basically computers, basically computer engineering. So when you encompass all these, like any robot or anything, that's a control system. So what are some of the examples? You have traffic signals. Of course, that's a control system. So you have seen those boxes of traffic signal where they go and they change the logic basically to control the traffic signals. That's a control system. It takes the input from the inductive coils that are under the road, and then you can use that input to set the timing of the signal. Or if you have a camera, you can see how dense is the traffic, how light is the traffic, and based on that, you can make kind of intelligent traffic signals. So all that is an example of a traffic control system, basically. All the rides in the theme park, they are a prime example of control systems. How you can create a ride using mechanical engineering, using electrical engineering, using computer engineering that can do a specific task. That's basically your control system. Most of the time, anything that you're creating in your senior design project, that is a control system, basically. Because again, most of you take wheels, take motors, do something, take sensors, microcontroller, electrical circuits, buck converter, boost converter, and put them together to create a control system. Ed, go ahead.
So how similar is this to using like PLCs?
So PLC is based on digital logic specifically. It is a control system itself, but that's based on digital logic. When you're controlling, even for traffic signals, if you're using PLCs or you're using PLCs in your theme parks, that is a control system. So you are, but that's a part of control system, because that's the electrical portion or the brain of your ride, let's say, which you have created using mechanical components, and then you have electrical wiring and stuff. And the PLC is used to program that ride, let's say, to operate in a specific manner. So that's one part of the control system, your PLC. The whole thing is the control system. Your whole ride, let's say, is the control system. And PLC is one of the major part of that control system. PLC is very, very important, actually. If you guys, right now you guys have to take PLC as part of your, I guess, program. I believe either you can take PLC or what you call the photonics course. I think my advice would be PLC is much more valuable to you than the photonics. No, don't get me wrong, photonics is good as well, but PLC relates more closely to the electrical or computer stuff that you do than the photonics course. So if you have to choose between the two, take PLC in the AS program. So a control system is an interconnected system to control a process from an input to produce a desired output. That's all what we do with control system. You have an input coming, you have to process based on that input, and then there's an output going. And generally, we want this input as our desired output. What we want the output to be, that is generally this input. And then whatever output is there, the actual output, whatever is there, then for example, if you are if you're steering a car manually, then of course when you turn your steering rightward, you want the car to go right. If you go leftward, it's car to go left based on how much steering you are turning. So your input in that case is going to be the angle, on the right or left, whatever you are. If you have the the reference is 0 angle, is like the straight, when the steering is straight, car is going straight. If you do it clockwise or counterclockwise, that's the desired angle you want the tires to turn to go right and left. Now, if you have, let's say, alignment problem or something, and your car is not going that much to the right and left, of course, you have to go and fix that thing. So that's an example of a manual control system in which basically the process is your car, or your steering system, and you are sending the input, and you're looking at visually inspecting where the car is going, and you want it to be pretty much the same as the input. If you're turning 20 degrees towards counterclockwise, you want the car to go about 20 degrees counterclockwise. So that's a manual control system. But that's an example of an open loop control system. There is an open loop control system, as you can see, and then there's a closed loop control system. So what is open loop control system? Here's the figure. You want the desired output response, whatever output you want. As I mentioned about the car, so you said, okay, I want the car to go 20 degrees towards left, and I'm moving the steering about 20 degrees. There's a controller, actuator, and process. These are 3 main components of a control system. And then the output. What is the actual output? You want the desired output to be actual output. Not necessarily it will be the actual output, because there are many factors that can affect the output, and it's possible that it is not equal to the desired output, which is your input. So if it is not, then of course you have to correct it. With the open loop system, the correction is manual. In the closed loop system, the correction can be automated. That's why closed loop systems are much more prevalent in the industry as compared to the open loop system. So what is the open loop system? It uses a controller, control logic, to drive an actuator. As you can see, action that a controller is taking to control a process. This morning in the DSP, I also mentioned actuators, which basically converts one form of energy into the other form of energy. So for the example that I gave this morning, for example, your mic is an actuator that converts the voice signals, the pressure, into electrical signals. So one form of energy, which is the pressure, it converts into electrical form of energy. So that's what the actuator does in general. So actuator usually converts energy into motion or a physical entity to control a process to obtain a desired response. So that's your open loop control system. You have a controller, whatever the control logic is, your microcontroller, whatever. You have an actuator, which the microcontroller is sending your signals to the actuator, which is converting one sort of energy into another sort of energy. And it is operating on a process. Processes in that case, as I gave you the example of your automobile or anything, that's your process. And then you're observing, hey, what's my output? If your output is exactly the same as your input, because your input was the desired output, your control system is working perfectly. If it is not, then you have to make changes to some of the parameters in your control systems. One of the common examples is a microwave oven operating for a specific amount of time. That's also microwave oven can be represented as a control system as well. Now, this is basically 99% of the system. Control systems are closed loop control systems. And this is a representation of closed loop control system. So once again, your input is your desired output. Let me grab my pen real quick. Oops. Okay. Let's see. Review. Okay. All right, so this is your input, which is your desired output. You have the controller, you have the actuator, you have the process. Same three things that were in the open loop control system. Now, at the output of the process, you have the actual output. So this was your desired output, which was your input. So if this is your, generally in this book, I think it's represented as R of t. And this is the actual output, which is Y of t. So the good thing about the closed loop control system is you have the ability to measure the actual output with the desired output to generate an error signal. If they are too different, there's too much difference between them, then your error signal is going to be high. If there's a little bit of difference, error signal is going to be low. But based on that error signal, you can program your microcontroller such that it can change its output to work on the process to bring this actual output as close to the desired output as possible. So this is all done through this feedback loop. So the feedback, actual output is coming through the feedback. It goes through a sensor. Sensor basically converts the actual output into the form of the output, which will be the same as the desired output signal. So it can compare against that. So if this is an electrical signal, and if this is a motion of the car, basically car is moving, then this sensor is going to convert this mechanical signal into the electrical signal to be compared against this electrical input that was coming in. So that's what the purpose of this sensor in the feedback loop. And the two signals are compared. Error signal is generated. So error signal is going to be difference between RT and the signal that is coming over here from the feedback loop. And from this error signal, again, you control the output of the microcontroller to bring the actual output, to basically work on the actuator process and bring the actual output as close to desired output as possible. So this is what we will be studying basically pretty much 99% of the time in this course, this model, pretty much. Now, in some of the block diagrams, this is a block diagram. In some of the block diagrams, some boxes will be combined together. So it may not have control actuator process. It's possible controller and actuator is in one box, and then process is the other box. Some of them, the sensor may be unity sensor. So the actual signal basically has the same form as the desired output. Actual output has the same form. So you just need a unity sensor. So it just passed through a unity sensor, or the sensor value is 1. And both output and the input will be compared against each other to produce the error signal. But this is the diagram, block diagram, that you will be using most of the time to describe a closed loop control system and to study the characteristics of the closed loop control system. Now, it's the same block diagram that I showed you, but now we have two more parameters over here. You have external disturbance. So anything external to the system is being added to the output of the microcontroller or any controller. I keep calling it microcontroller, but it can be any controller that is sending the signal to the actuator to run the process. So any external any noise signal externally to the system that is affecting the system to the actuator, that's called disturbance. So as you can see, that disturbance is added to the signal coming out of the controller. And then there is another input, which is measurement noise. And this is internal to the system. Noise which is coming from inside the system. And that again is added to the actual output to kind of distort that output, which is going through the feedback loop. So those are present in most of the rail system. You have the external disturbance and internal measurement noise. So again, we're going to look at, in the presence of those two quantities, how we are going to work on a control system. It's possible one quantity is present, the other is not. It's possible both of them are present, and it's possible both of them, we assume it's an ideal system, and we assume these quantities are not present. And when we start the discussion, that's what our assumption is going to be, that we want to take it ideally, and we assume no disturbance and no internal measurement noise, and then we're going to look at this. Ed, go ahead.
Is the disturbance, is this like EMI disturbance?
Any disturbance outside the system. It can be an electromagnetic disturbance. It can be some sort of mechanical disturbance to your system. Anything which is not desired to the system, but it is affecting the system from outside the system. Can be any disturbance. Okay, so closed loop feedback system generally employed for their superior measurement noise attenuation characteristics, and ability to reject external disturbance signal. They mentioned, so closed loop work in a better way to kind of take care of these two parameters. External disturbance and measurement noise are always there in the real world application, and of course must be addressed in the practical control system design. As I said, some of the control system we will have those things, and some we will assume they're not there, just to study how to deal with that control system ideally. Now, this is a multi-loop control system. And a multi-loop control system, again, you will do some problems using multi-loop control system. So as you can see, there's an outer loop, and then there's an inner loop. So now you have two loops. You have two controllers. You have actuator, process, and sensor for the inner loop. And then you can solve this inner loop first and replace the whole thing by a single block, as you will see when we do that. And that single block basically will be in series with this controller 2 and this sensor 2 in the feedback loop, and then you can solve for the outer loop. So it is not very hard to solve multi-loops control systems. You just have to do it in steps. First, go to the inner loop, solve that, replace the whole inner loop by one, like you do, like your equivalent resistance, let's say. So you have a bunch of resistors connected in series, parallel, and stuff. So you can replace all of those by a single resistor. The same concept is over here. The inner loop can be replaced by a single block. And how we do that, you will see in chapter number 2 or 3 and stuff. And once you will replace this, then of course you have only a single loop, and then you can go ahead and work on that. And give me a second. Okay. All right. So there will be a few problems like this. Now, I don't think we will be doing problems with multivariable inputs. So again, control systems, and I guess, Andre, you were talking to me earlier this morning, and that's why when you were discussing about those, I mentioned it to you that that's a control system with multiple inputs. You have the 5 sensors input coming in and stuff like that. So this is the example of multi-input system. So you have multiple inputs coming in instead of a single input. So again, input means that this is what you want at the output. Those are the desired output. Those are our inputs. So if you have multiple inputs coming in, so you have, like, let's say temperature, you have pressure on some system, you have humidity or whatever. So let's say you have a weather station, weather control system, and you are measuring different things, and based on that things, you are doing some control system to perform some signals at the output. So based on whatever is coming in, you can have multiple inputs coming in, and you want to see what are the outputs. So for each input, you have one output going out. In this case, you want the output to be as close as possible to the desired input. So if it's a temperature, you want to match the temperature with whatever you want at the output. So if it's like an AC system, you are setting your thermostat. Actually, in AC system, basically you're setting your thermostat, and that's the only desired output. So it's not really a multi-input variable system. AC system is just a single input variable system. But you can have, again, different systems with multiple input that you want at the output. So as you can see, instead of single signal flowing, you have multiple signal flowing throughout the system, one for each input that you want at the output. So these type of systems are also there. I'm not going to be doing, I don't think I'm going to be doing any examples with multi-input, because again, it's just become too complicated to analyze at certain points. So just want to mention that these systems are there, practical systems, but I don't think we'll be doing problems based on multi-input. We will be doing problems based on multi-loop system, but not multi-variable systems. Some of the history that I picked up from the textbook, and put it here. As you can see, 1769 is pretty much what's the recorded date of the start of control systems. Although I believe the control systems, they're not documented, but they've been going on since the start of, I'm assuming, the start of this universe. I mean, everything that somebody has created, even from very primitive things, that's a control system. If it's doing something, you can basically characterize it as a control system. But the recorded history, as you can see in your book, it's starting from 1769, James Watt's steam engine and governor developed, and then 1868, 1913. I don't want to go over each one of them. Observe this name, Nyquist, as we were discussing this morning, Nyquist. You're going to be looking at Nyquist in this course as well. H. Nyquist developed a method for analyzing the stability of systems. So as the same Nyquist that we were discussing in DSP as well. So again, I don't want to really go that from all the way 2019. And I'm assuming the book, when it was published, I'm assuming I did pick up this table from the new book, but it's possible I picked it up from the old book because it's just ending at 2019. It's 2023, so some major advances must have been made in the control systems application. No, not the theory. Control system theory really didn't change much, but the application have been changed a lot. So again, they're just putting the different applications. GPS is a multi-input control system. All right. What we can do is 1 hour 15. Actually, no, I thought this class started at 5 o'clock. It's only 45 minutes. So we will keep on going, and let's see if we can finish it actually before the first break. Then all of us will be happy. All right. Control system design. Let me kind of increase the. Okay. So what are some of the specific key parameters to design a control system? They are given in this diagram, flowchart. And again, this is from your book. The first thing that you do is you establish what your control system needs to do. You have to establish the goals of the control systems. Then you have to identify what are the variables that are involved to establish those goals. Write the specifications. Now, if some of you have taken senior design proposal course, or I don't know if somebody is here who's doing the project, but you will see basically pretty similar things when we do the senior design. You have to establish the requirements of the project, which are the goals of the project. You have to write the specifications of the project and all those things. So that's basically you are creating a control system module. So you establish the goal, you identify what type of variables are involved to make those goals successful. You write the specifications of that. Specifications are basically if you are using some system, you're using a microcontroller, let's say, then how many bits do you want for that microcontroller? How many input-output do you want? What should be the speed, the processing speed? Those are the specifications. So you establish the specifications. Generally, you don't specify, I want a Raspberry Pi this model. That's not a specification. A specification is what are the general characteristics that you want for any things that you're using in the control system. And based on those specifications, you go and choose if there's an IC, if it's a microcontroller, if it's a sensor, then you go and choose that specific equipment. So specifications are in general, without the name of your microcontroller IC and stuff, just what do you want in that microcontroller? Because it's possible based on your specification, you can choose 10 different microcontrollers. And then you're going to go with one specific one based on, you will say, well, this satisfies my specification, so I'm just going to go ahead and choose this. And it has, less power consumption and stuff like that, let's say. So once you choose the specification, establishment of goal variables to be controlled in a specification, then the second step is system definition and modeling. Establish the system configuration, obtain a model of the process, actuator, and the sensor, which is in the feedback loop. Describe a controller and select key parameters to be adjusted for the microcontroller or controller. I keep calling it microcontroller, just a controller. And of course, based on your error signal, you go back, that's the feedback loop, you go back, and then you change the system configuration based on the error signal. What is the error signal? The difference between the desired output and the actual output. That's the error signal. So this is, 6 steps, 7 steps of creating a control system from the bird's eye view, like big picture. So let's look at some of the examples. This screen is hard to move. Okay, I'm gonna put it somewhere on top. All right, here you go. Okay, so example 1.1, an automobile steering control system in a block diagram. Now this is a feedback control system. So in a regular automobile, not self-driving automobile, of course, self-driving is another control system, but this is a regular automobile. You are the controller. If you're driving it, you are the controller. You are controlling that automobile. The steering mechanism is the actuator. You are putting force on the steering, left or right, creating torque. And that force is converting into changing the direction of the steering, basically. So steering is your actuator. And of course, your process is your car. So you have to go in a desired course of travel. Let's say you're going straight, you're keeping the steering straight. You're the controller and actual course of car. So as you can see, desired direction is this. And let's say your alignment is bad. And instead of going this direction, your car started going this direction. So what you're going to do? Of course, this is going to come back. You're going to look at visually, tactile and visual. Hey, I want to go straight, but the car is moving towards the right or left. What you're going to do? You're going to move the steering. The error is going to be generated. That okay, the actual direction is not the desired direction. That error, based on that error, you, who is the controller, is going to change the direction of is going to put pressure on the steering, left or right, and try to assume the actual course of travel, the desired course of travel. So in this case, basically it is a system, which is the feedback system, but the sensor in this case, this is the sensor. The sensor in this case is your eyes that you can see, and you can look at the meters and stuff as well, which direction you're going, but generally it's a visual inspection of in which direction you're going. So that's a very manual control system. One step ahead is, of course, let's see what is next. Okay, so the cruise control is going to come next, I guess. Again, kind of manual control system, and all these manual control system again can be created fully automated. So your self-driving cars, you're not the controller. Your self-driving cars, the signals that are coming from your sensors that are on your Tesla or any other car, camera signals from the camera, signals from the IR sensors, radars, and all those. I think Tesla removed the radars actually. But all those signals are coming in to the main processor, and based on that signals, basically, it is controlling the steering wheel. So in that case, you're not the controller in a self-driving car. The signals that are coming in through the microcontroller is the controller actually. Well, microprocessor, microcontroller, or computer, whatever. But this is the manual system. What is this? All right, so this diagram, it represents a control system where an operator is using a valve to control the flow of liquid from a tank to keep the fluid level regulated, right over here. So this operator basically is inspecting the fluid level visually, and he wants the fluid level to be a specific height in the tank. If the fluid input starts filling up the tank, then of course he is going to open the valve to let the fluid go so that it will stay at that specific level. And of course, if there's no fluid, then of course it's going to close the valve so that it will stay at that level. So that's the control system. Again, it's a manual control system. It can very well be made an automated control system very easily. But for this manual control system, you have the desired fluid level, which is your desired output response. As you can see, your controller is this guy, operator. Actuator is this valve mechanism. He's turning that right or left to control the valve. And of course, process is taking place on this tank. Actual output is the actual fluid level in the tank. And he's going to inspect it, visual inspection. And again, if the actual fluid level is higher than the desired fluid level, it's going to open the valve to let some of the fluid go. And if it is equal to the fluid level, it's going to close the valve. If it becomes lower than the fluid level, then of course, it's going to close the valve and let the fluid gather in the tank until it becomes to the desired level. So again, in terms of a control system, it's a manual control system. And these are actuator, controller, and stuff for this control system. And as I mentioned here, the system can be made totally automated with a microcontroller replacing the operator and some sort of relay system that can be used as a sensor. Yeah, this system is very common actually. Most of the water storage systems, you have a pump basically that can pump the water, and based on the height of the water level in the tank, the pump can turn on automatically or turn off to maintain the height. So this system is very common, and it is a very common automated system basically to keep the fluid level same in a water tank. So those systems that we discussed were the manual control system, a system completely operated by human. Both systems that we discussed, one manual control system. You have automatic control system that there is no human intervention, and totally automated system. Again, many of the systems these days, starting from the smart cars to ride control systems using PLCs and all those are automated control systems. They keep detecting the error and keep adjusting themselves to operate as they're supposed to operate. And of course, there are exceptional conditions that if this exception happen, turn the ride off or do this or do that. So those are totally automated control systems. And many systems are semi-automatic, like your assembly lines, automobile assembly line, where you have the robots doing a lot of things, plus humans are there to assist in the building of an automobile or stuff. So that's a semi-automatic control system. So all three of them exist. Automatic, of course, and semi-automatic, they are much more of interest rather than manual control system. All right, let's see example 1.3. Simple system where a battery is connected to a variable resistor to provide a specific voltage to a DC amplifier connected to a DC motor, which is rotating a disk. I don't know, what did I write over here? All right, a simple system where a battery is connected to a straight variable resistor to provide a specific voltage to a DC amplifier connected to a DC motor, which is rotating the disk will work. I don't know what I was trying to write over here, but basically it is a rotating disk. You can assume it to be a CD player or something, and based on the voltage that is coming into the motor and the current coming into the motor, it will increase or decrease the speed of the rotating disk. I'll have to fix it. I don't know what I was trying to write. So based on the required speed of the CD input variable, the battery voltage can be set through rheostat to drive the amplifier to provide the desired amount of voltage and current to the motor to control its speed. This is an open loop control system. As you can see, there is no feedback. You need desired speed, which is sent by specific voltage to the controller, which is this amplifier, DC amplifier. And that is going to send the current, higher current or lower current, based on what speed do you want, to the DC motor, and it's going to start rotating that disk at that specific speed. So observe that there is no feedback. So we are assuming here that actual speed is what we need. If it is not, there is no way for us to rectify this system. So that's one of the biggest drawback of open loop systems. If your output is not equal to the input, really there is no means for us to fix that output. But many times, open loop systems are easier to build, first of all. And many times the chances of error are extremely low. In those cases, there is really no need for the feedback control system, and open loop control systems can be used easily. And this may be one of the cases, because if you know exactly, and of course, you can do the calculations very easily, that for a specific motor that requires this much voltage, this much current, this much torque, how much voltage needs to be supplied to that motor, how much current needs to be supplied to that motor for the motor to rotate at a specific RPM. And you can easily calculate that. And in that case, you can provide that voltage, and it will rotate at that speed. Of course, you're not measuring the speed. There is no, again, as I said, feedback. But we assume that the speed will be fine, because that's the job of the motor, that at that specific voltage or current is going to rotate at that specific speed. So this system, open loop, without feedback, may work. Who knows? May work without much error, that is. Same thing, but with the feedback loop. So now you are adding a tachometer in the feedback loop. That's the sensor. So you're measuring the actual speed, and the tachometer is converting that speed into the voltage signal, into the electrical signal, which is measured against the desired speed. If they are same, the error is 0, or if they are very close to each other, error is very small. That means the actual speed and desired speed is very close to each other. If they are not same, the error is going to be large, is going to make the amplifier send higher amount of voltage or current to the DC DC motor, which will speed up the rotation of the disk. So if the error is positively large, that means actual speed is less than the desired speed. If the error is negatively large, that means the actual speed is more than the desired speed, because remember, you're subtracting this desired, the actual from the desired speed. So the error can be positive or negative. If the error is negative, means desired speed is less than the actual speed. In that case, whatever the error signal is there, the amplifier is going to reduce the voltage that it is sending to the motor, reduce the amount of current, and the speed of the motor is going to be smaller. It's going to slow down, basically. So that's the example of the same system that we had, but using a feedback loop, using a tachometer as the sensor to make the system fully automated. All right, another example. Design a system to regulate the blood sugar concentration level of a diabetic person by controlling dispensing of insulin. And again, this is a very commonly used system. Many people who have diabetes, they use this type of system. This type of system can be open loop, timer based, that it will dispense a specific amount of insulin at a specific time without actually measuring the blood sugar level. And many systems are closed loop, that it does measure the blood glucose level, and based on that level, it dispenses the amount of insulin that is required for the body. So both systems exist actually. Open loop system exists as well as closed loop system also exists. Many of the people actually use open loop system because they say, oh, we take insulin only at this specific time after we eat, lunch or dinner. So only at that time, they want to dispense a specific amount of insulin. Again, they're not measuring anything, or they're measuring manually, and based on that, they're adjusting the amount of insulin that needs to be measured. But that can be kind of, they don't have to do that if they're using closed loop system that will measure the insulin level automatically, and based on that, it will adjust how much insulin need to be dispensed, and when it need to be dispensed, that can be set through the closed loop systems as well. So both systems can be created. They do exist, as I said. And these are the block diagram of those systems. The top one is the open loop. So you have a microcontroller program, signal generator, basically, that is specific time, start sending the signal to the motor, pump, and valve to dispense a specific amount of insulin. And in the feedback loop, you want your glucose level to be a specific value. And again, you're sending the signal, microcontroller, amplifier, motor and pump, insulin delivery rate, and your process is human body, of course. And after it dispenses the insulin, then you measure the actual glucose level. Not you, but the system measures the actual glucose level. And based on that, it sends the data back through the sensor. And then it is compared against the desired glucose level. If it is low, high, based on that, the insulin amount is adjusted. So as I said, both systems do exist. And many people use simple system, very simple system, manual dispensing, and without a feedback loop, and many people do use that. I've seen many people actually using the simple, because they say, okay, we only dispense at a specific time, so we don't really need to have a closed loop system. Closed loop system is more active, basically, perhaps people who are acutely diabetic that need to monitor their sugar level all the time. Because I think one of my uncles used the open loop system. And one of the last examples is a cruise control system in an automobile that can make the car moving at a prescribed speed. And everyone has used cruise control. I'm assuming everyone has used cruise control in their car. So you have a desired speed, and you have a microcontroller, of course. In this case, actuator, I'm putting fuel injector system, because how much, again, gas cars, not the electric vehicles. How much fuel is going into your engine, that will determine the speed, how much you're burning, basically. An automobile engine is the process where the burning is happening. Of course, if it comes down to the electric vehicle, then you're going to change those things to your how much current the battery is supplying to the motor, basically. So your actuator is going to become your battery. How much current it has to supply to your motor to run the motor faster or slower to keep the desired speed. Now, this is not the adaptive. I don't think this is adaptive control, cruise control. It is just a regular cruise control that keep monitoring the actual speed, and then compare it against the desired speed, and based on that, basically you can change how much gas has to be given to the fuel injector. This is actually the manual control system because you're using a speedometer to observe how fast you're going. Well, it can be manual or it can be automated because speedometer can be used for both. You can either use visually and then adjust that, or if it is totally automated, then of course, a speedometer output can be used as a signal, automated signal, to compare against the desired speed to adjust the controller output to the fuel injector to reduce the speed or increase the speed. And the final example for today is thermostatically controlled air conditioning system that I mentioned a while ago of an automobile where a driver sets the temperature on a dashboard panel. So you want a desired temperature. It can be your automobile, it can be your home, wherever. Your AC, basically, your desired temperature, whatever you want. And you have the thermostat, which is your controller, air conditioning unit. And in this case, automobile cabin is the process. If you're using home, then of course your home or your room is going to be the process on which the actuator is working. You're measuring the temperature using a thermometer or something, or temperature sensor, not thermometer, temperature sensor. And you're comparing it against the desired temperature. So temperature sensor is basically converting the actual temperature into your electrical signals to measure again the desired temperature. Based on the error, of course, you can control the thermostat, make it cooler or make it warmer so that your cabin is going to stay at a specific temperature. So this is basically your adaptive air conditioning system, where you can set it. The older cars, of course, they didn't used to have that. You can just set a temperature and it will just keep blowing the air irrespective if it is much cooler than what you want. So in the older cars, like I have one old car, and there is really no adaptive control, adaptive air conditioning system. You can just set the fan speed, you can set how much cooler do you want, and then it just keeps on running. But most of the newer car, you can set the temperature, and then it will hold the temperature for the duration of whatever you want. So once again, recapturing what we did today, because this is the last thing that we are doing today. It was a pretty short class. I don't think classes will be this short starting next week. So the basic thing that we did today is we looked at how to represent a feedback control system using this block diagram. There are four basic components of a feedback control system: controller, actuator, process, which produce the output of the system. That output in the feedback loop goes through the sensor, which produce the signal corresponding to the output that can be compared against the desired output. Whatever signal is that, electrical signal or whichever. Mostly it's the electrical signals. And then based on that, the controller adjusts its output to control the actuator to work on the process. So that's our basic feedback control system that pretty much we're going to be using throughout this course. So make sure anytime we're going to be using the control system, you will see this type of diagram. As I said, controller, actuator can be combined together. Actuator, process can be combined together in one block. But in general, you have this system with the feedback loop. Feedback loop can be a unity feedback loop. Many times we're going to be using unity feedback loop with the gain in the feedback to be one only. And many times you have different gains in the feedback loop. So we looked at different examples of how to create this block diagram for different type of practical control systems. We look at multiple control system, multivariable, multi-loop control systems. And then we discussed open loop system as well as closed loop system. Closed loop system, as I said, are 99% of the systems are closed loop system, as I mentioned. Very few systems are going to be open loop systems. But yeah, so this is basically some basic introduction about what we're going to be doing in this course, what is control systems, how we can put together different control system in a block diagram form that we'll be using again to characterize different control systems. If you have any questions, so this is pretty much it for today. This is the first chapter.